Good morning, everyone. Thanks for joining me today for my presentation. Yep. So I'm excited to share my experience and journey with you on developing a solution, which was a recurring problem for us. So, bit about me. I am Aman. I'm from India, so this is how they spell my name in Hindi. I'm a senior computer scientist at Adobe in San Francisco, where I have been working for the last 18 years. Majority of my work is on C++ code base, which I use to develop cross-platform applications for Windows, Mac, iOS, and Android. I also work on JavaScript components, both on the back end using Node and front end. And on Node, again, most of our components are written in C++, which are exposed to the JavaScript world through NAPI layer. I began my career working on embedded systems, specializing in navigation and weapon integration for fighter aircrafts. So that was very exciting. This experience has given me a deep appreciation for the intricacies of software development in demanding components. I first learned C++ during my college days back in 1998. And my passion for the language has only grown since then. If you need to reach me, feel free to reach me at either adchawla@gmail.com, that's my personal email ID, or my professional, which is amandeep@adobe.com. So let's set some ground rules. Feel free to interrupt and ask questions. The code shown on the slides is in a slides-aware format. So it's just intended to convey concepts rather than be directly runnable. In normal code, I can promise you that I advocate for the use of these keywords as much as possible. And because of screen space constraints, I have to remove a lot of those keywords in my slides. But wherever I have the real estate, I actually kept it there. So just be aware that, but the repo has all the keywords in place, which I will be sharing with you. So the agenda. Today we will be exploring finite state machines in depth, covering the following key areas. Brief understanding of finite state machines. We will start with what FSMs are and how they function. We will discuss an example of finite state machine. We will walk through a practical yet fictional example to illustrate how FSM work in real world scenario. Evolution of finite state machines, implementation techniques. We will discuss the progression of implementation techniques for finite state machines, including the naive approach using enums and switches, using state patterns, and utilizing STL variants for flexibility and maintainability. I will also be showing you some benchmark results. So we'll go into some performance numbers and compare their performance. So what is a finite machine? According to Wikipedia, it is an abstract machine that can be in exactly one of a finite number of states at any given time. So your system can have multiple states, but at one point it can only be in one of the states. So that is a finite state machine. It can change from one state to another in response to some inputs. And in our terminology, we call them events. The change, and that change is also called as transition. It is, and the finite state machine is defined by a list of states the system can be, its initial state, and all the transitions which happens, means which event leads to another state. So that is what finite machines is. So all these three statements effectively capture the essence of how finite state machines operate and transition between states based on inputs. Now let's take an example of turnstile placed at subways to charge your account for travel and regulate flow of people onto the platforms. So this is how the state diagram of almost practical turnstile looks like. I have taken away some of the intricacies, but on the top, our system comprises of 5 states, which are namely locked, where it is not letting people to go across the turnstile. And the other opposite is unlocked, where it is letting the person to cross the aisle. And then there is a state called payment processing, where actually once the person has presented his card, it moves to payment processing, and then the payment processes tries to connect to the backend payment gateways to see whether we can charge that account for that much amount which is required. And payment failed and payment successful, those are transient states or intermediate states, we call them. They are there for a few seconds just to display some information, and then they eventually lead to their next state, which is in case of payment failed is logged, and in case of payment successful is unlogged. But they display some piece of information which we don't want to keep there for a longer period of time. Any questions on the state machine? Another one thing I missed was payment processing is configured that on a timeout, once it tries to connect to the payment gateway, it tries multiple times. So we have configured it, let's say, with 3 gateways, that these are the 3 payment gateways you should try in a priority order. So it tries the first. If it doesn't get any response back, that means the network is not, we are not able to connect to the payment gateway. It tries another one, then the last one. And after all the retries, then also it fails, even though we didn't get any transaction declined, even from the system itself. So this is how this fictional finite state machine we will be implementing. So any questions on this? Yep.
Sorry, so what's the difference between retry count equals 3 versus less than 3?
Yeah, so every time when we try, we start with a 0 retry count. So if we are 0, 1, 2, we will be going to retry.
Less than 3 processing is looping.
Yes, we are looping. So we are going to the payment processing state itself, but only if we either get a transaction declined or 4th timeout.
Okay.
Then we will go to the payment failed.
Thank you.
Any other questions? So please keep this in your mind little bit, that how this whole, what we are going to implement. So let's set up some ground rules, which is common to all implementations. So we will establish some foundational aspects which are needed to for the operation and control of the turnstile. And so our turnstile also connects to external devices. And one of 2 of those devices are swing door and LED display. So the swing door can be either in an open or closed position as shown here, so that it actually stops the flow of the person, or it can let the person go. The LED display provides visual and some possibly audio outputs also to users, indicating whether they can pass through. So importantly, if you see, these 2 devices are synchronized by our finite state machine implementation. For example, if the door is closed, the LED shows green arrow. And if it is closed, it shows red cross. And when it is open, it shows a green arrow. So they are synchronized, but they don't have this logic in. Our implementation will be controlling this aspect. In actual scenarios or in actual device, when we integrate, they are not just output devices which we are controlling, but they also send us some signals. For example, as soon as a person passes, it sends me a person passed event, which the system actually then processes and moves to the next state. But since we are simulating the stuff, and so those events we will be generating through code only when we are testing it. And this is how we are going to model. Our swing door will have a status, whether it is a closed or open. And there are 2 functions on it, to open and close. So they set appropriately the state, and to read the status. That status is mostly for our test cases, when we will be writing the test cases to test them. And similarly, the LED controller has 4 states. The red cross means you can't cross. Flashing red cross means we were not able to process your card for any reason. And mostly it also have emit some beeps also. And the green arrow is to let the people across. And orange cross, we will see what is the use of that. And similarly to swing door, we have 2 functions on its set status and get status. We will also be integrating with the point of sale terminal. which plays a crucial role in reading the TRAD and initiating the TRAD presented event in real scenarios. So our system communicates with the POS terminal to specify the payment gateway. So POS terminal in this case is not very intelligent device. We tell them that which gateway to connect and how much amount to deduct from the person's account. The POS terminal in real world will respond back with events, for example, transaction successful or transaction declined. And most of the time it also takes trails of timeout. But as I said, we will be simulating those events. Devices are like, for example, we are just treating them as output devices. So this is how we are going to model the POS terminal. So as you have seen in this, it can show 3 lines of text. And this is how we are going to control that we have set rows function, and then we can read each row through functions. Any questions till this time? Okay. And we have 5 events. The first one is TRAD presented. As soon as a person touches the TRAD on the POS terminal, if the POS terminal is able to read that TRAD, it generates the TRAD presented and provides the TRAD number information, which we need later on. Transaction declined will also give us the reason that why the transaction was declined, so that we can show it on the POS terminal. Transaction success tells me, oh, this is the fare and this is the balance left in the person's account, so that we can show it on the POS terminal again. And person passed, we don't need any data with it. It's just when the person passes through the turnstile, it emits the person passed event. And timeout is internal, where we use timeouts for retrying while we are payment processing, or when we are moving from transient states out to their net states. For example, when you are in payment failed, you just want to show the information that why the transaction was declined for some time. You don't want to be in that state forever. So that as soon as the person goes away from that terminal, that information is also drawn and it's back to the logged state. So ways to implement. So we have several options for implementing our state machines, and those include using if-else statements and Boolean variables for each state, utilizing enums and switch statements, employing standard variant, leveraging the boost libraries, and implementing with coroutines. We won't be considering the if-else approach, as it intends to introduce more bugs and complexities. And especially in machines with multiple states, it's like a hell dealing with those if-else. And as soon as I see a code in in any of the things I am reviewing, if it's the state, I will never let it go through that. If-else using for anything which has more than 2 states is always a doom. You will run into some issues later on. So similarly, we won't cover the boost and coroutine implementations, as standard variant has proven to be sufficient for my use cases. So standard variant give me all the flexibility I needed as well as the performance I wanted from my system.
So,
yeah.
So what specifically do you mean by boost?
So boost has I think 2 libraries which deals with the state machines.
I see.
Yeah. Any other question? Okay. Let's go through how the finite state machines using enums are implemented generally. So on the top level, you will have some enum which defines all the states we have. For example, logged, payment processing, payment failed, payment success, and unlogged. They correspond to each state we have in our system. And this is how our finite state machine looks like. So we have 5 overload process functions, each corresponding to one of the 5 events in our system. So we have process start presented, process start transaction declined, transaction success, person passed, and timeout. We have a member variable which is used to track the current state, which is by _state, initialized to logged during construction. So every time when we create this FSM object, our initial state is always logged. The model includes interface with 3 external devices. So we have 3 devices: swing door, POS terminal, LED controller. So those are the three devices which we will be controlling also through our finite state machine. This model has to behave like if you see the states data, read-write rounds is only specific to when I'm in payment processing state. It does not apply when I'm in a lot state or unload state. But in this implementation, when you are using enums, your system has to act like an algebraic product type. It has to have all the data members in all the states. And that is the root cause, major root cause of all the bugs which we will see. This is how the process function will look like when we are moving from unload to payment processing. So process function will see if I'm in load state, I will call an internal function called transition to payment processing, give it the gateway and the card number. And transition to payment processing will trash the card number because we need it when we are retrying every time. And then we will call an external function called initiate transaction, which will actually make a call to the payment gateway. And then it will set up what all needs to be done for the state. So for example, in this state, we have to make sure door is closed. We have to, on the pause, sets that we are processing. And LED status is orange, that we are processing this thing. And state, we move to payment processing. Similarly, when we are doing transaction declined, it's the same way. We just move to, 1 minute. Yeah, we call transition to payment failed because that's the next state for transaction declined. And on transaction success, if we are in payment processing state, we move to call a function transition to payment successful. And similarly, these whole functions are defined. The interesting ones are, see, whenever we are making a transition, we have to call the functions, we have to set the devices properly. So this code is getting repeated multiple times. Plus later on we will see what the problems it can pose. And this is the complex one, where the same event is handled by multiple states, if you see. So if I'm in the payment processing state, I am incrementing my read-write count, and yeah, if it is greater than 2, I say I am transitioning to payment failed. Otherwise, I am reinitiating the transaction with the next gateway. In case of timeout, when I'm in payment failed state, I move to transition to lot because it's a transition state, as we know, and payment successful in payment success state, I transition to unload state. So any questions on this? It's pretty straightforward that what all was there in the state diagram, we are just implementing here. Now, this was the test. So we start with the lot state. I'm expecting that the initial state has to be payment processing, and I'm also making sure all the external devices are in the right state, and then I'm sending so this is the test payment processing where we just present the card processing of this thing. So we have on the second line in the test, we have FSM.process, so we generate that event, and we are making sure that we are in the right state with the right devices. Each device is in the right state. And if you see the console output, initially we started with lot state, the door was closed, LED was red cross, and POS terminal was just displaying touch card. And then the event came card present, and the actions, which external actions we performed. We initiated a transaction to gateway 1 with card A and for amount $3. State, we moved to next state, which was payment processing. The door is closed, LED turns to orange, and POS terminals displayed processing. So everything is working as expected. So let's have a small quiz time. Based on whatever state we have, what state machine we have implemented. What is the state when I say question 1, and what is the state when I say Q2? Any guesses? So we start with the lot state. First, we presented, we move to payment processing state. First time out, we are still in payment processing, we just move to gateway 2. Third time, again we are still in the payment processing and we move to the gateway 3. And still no response, we move to payment failed, with the reason being network failure. We were not able to do anything. And then timeout, we move from a transition state to back to logged. Everything in sync. Again, someone presented a card, and we move to payment processing. And then at timeout, what should be our state? So if I'm in the payment processing state, first timeout happens, what we do?
You stay in the same state.
And retry, but it says timeout. And similar thing is when I'm running my tests, this test fails, which I say test bud, and it says rather than having a state of 1, which was payment processing, rather than in payment processing state, I'm in payment fail state 2. So this is the problem with implementing any product type data structure. So the issue is in this function. When we are transitioning to payment processing, we didn't set retry count to 0. And that is the problem when you have a lot of data members and you might be first time when you implement it, you will not have any issues. But later on, after a few months, after a few years, someone add a couple of new variables. And because it's a product type, you will always run into this state. So the only fix is we just have to do this change. And then the thing starts working fine. So now our tests are fine, we are good, happy. So with enums, the typical bugs are that we fail to reset variables belonging to a state on a transition. Because these member will keep on adding. Even you will not see the problem initially when you are writing the code, but after some time, this is bound to happen. Another problem with our implementation is we are not canceling or resetting external actions, for example, timeout. We haven't yet played anything with the timeout here. We haven't initialized the timer. We haven't canceled the timer. We haven't restarted the timer. What all is required. So this even has that bug. So if you see, even without timeout, the things are so complex, and if we add timeout functionality, the things will grow more bad for us. So let's sum up the finite state machines using enums. So the advantages are we don't use any heap, so that's a good part. So everything is happening on stack, so no dynamic allocation is in picture. Simplicity. The approach is straightforward, especially for simpler state machines, without complex state data. That is very important part. If you don't have much of state data, enums might be a good option for that. But as soon as you have started getting state data, this is not a good implementation. Disadvantages. States are simple because enums can't carry data with them. So state machines tends to actually converts to algebraic product type. The problem with that is the variables which we don't even need stay in scope more than what they are required. And that increases memory footprint also. Difficulty in extensibility. Adding new states or events can be challenging. Because if you see, every time when we add new event, we have to add another overlay. Whenever we add in state, we have to change the enum and then add all those processing functions, the logic for that, in the same function. So you are always modifying the functions. And the biggest problem I have is shared responsibility. The switch state, the functions, each function caters to multiple states. If you see, it has to see that this state I have to do this logic, if this is the state I have to do this logic. And that is always a maintenance overhead. So let's see finite state machine using state pattern. So everyone must have read design pattern books, Jan 4, and it has a state pattern. And it's actually a very good design. And let's go over that in little bit detail. So here the actual machine, the context which we call, doesn't implement state-specific behavior directly. It doesn't deal with the states specifically. It just has a reference to the state. So context delegates to the state interface for performing state-specific behavior. So it calls state.handle, which makes context independent of how state-specific behavior is implemented. The concrete classes, like in this example, concrete state A and concrete state B, these classes implement the state interface. That is, implement the state-specific behavior for each state. So this is how various actors in the state pattern looks like. And we can use this technique to implement our example. So let's go over it in a little bit detail. So we first have to define a base state, because that's the interface which our actual finite state machine is going to use. So it have 5 virtual event handlers corresponding to each event. These functions return an invalid pointer if the state handles an event but does not require a transition. For example, in payment processing, first retry, it doesn't require a state transition. So it will return an invalid unique pointer. Otherwise, they return a unique pointer to the next state. The state interface requires sometimes, or most of the times, all the implementations I have done in the past, requires a reference to the actual machine, because for even in this example, external devices are part of machine, not part of this. So the states do need a reference to the actual machine so that they can delegate those functionalities to those functions provided by that context interface. We also have a virtual get state that is again just for testing to make sure that I get an enum back and I can test whether I'm in the right state or not. Okay. So this is an implementation of how lot state will look like. Upon construction, it sets all the devices at one place, at one precise place, that as soon as it is constructed, it gets the context. On that using that context, it sets, make sure that each device is in the proper state. And it is only interested in processing card presented event. It is not interested in any other event. So it will just return a net state, which is payment processing. Because if you have noticed, the default implementation of our handlers, event handlers in the base state, they will return in null pointers. So all the other events will be ignored automatically. I think I missed one part. You have to use using here. Otherwise, they are hidden. But do I need it? No, I don't need it. Yeah, it's fine. Yeah. Because I never deal directly with the implementations, I deal with the interface. Similarly, payment processing. This is a little bit complex, as you have seen. It has, first thing is it handles 3 events. And then based on the timeout, it responds differently. But this is how the state looks like. Now, read-write count is part of this state. It's not part of the state, the top level class. Card number is part of this thing. And it has a timeout manager. It deals with the timeout. This implementation has a functionality. Whereas whenever we are initiating payment processing, if you see, we are initializing the timeout manager, giving it a function that please call this function. And after 2 seconds, so we have a duration of 2 seconds. And we set all the external devices properly. And this is how we handle all the 3 events which I am responsible for handling as per this state. Transaction declined, which moves it to payment failed. Transaction success, which moves to payment success. And on timeout, again the logic is if retry, I increment the retry count. If it is less than all the gateways, I keep on retrying. Otherwise, I will move to the payment failed state. So this was one of the complex ones. Others are very simple. Payment failed. We set the devices properly. And on timeout, we move to the lot state. It does have a reason. and a timeout manager, because it also needs to crawl the timeout, that please create a timeout for 2 seconds, so that after 2 seconds, as soon as I receive a timeout event, I move to the lock state. Payment success, same way. It sets the 3 rows of the POS to the right state, like what is it is approved, this much was the fare, and this much is the balance. And also initiates the timer, and then on the timeout event, it moves to the unlock state. Another thing to note is, even though as soon as I'm in the payment success state, I should open the doors. I should not make the person wait for 2 seconds so that it moves to the unlock state. So that's why it also handles person passed event. So if I get person passed event, I directly go to lock state, bypassing the unlock state. And in case of timeout, I may move to unlock state, so that in that it can wait till the person passes. Because I don't want to have this fare and balance information for much longer period. Just it is required for 2 seconds, just to give an indication. So that's the idea. Unlock, it's almost same. It makes the door open, sets the status to green, and set the row to approved. So it removes the fare and amount information. And this is how our finite machine will use all these things together. And so you have a finite state machine. It makes sure your member variable state is set to lock state during construction, and provides a reference to it itself. Here we are using template generation machinery to generate functions specific to each event. So this will generate an event based on each event type. And what it does is it simply pass on that information to the state, whichever is the current state, which processes it. So this class is oblivious to the fact that how many events our system has. The states are ones which are tied to the events, how many events we have in the system. And that's it. It creates 3 connected devices, and we can get those devices because states need those devices to set the proper states on those external devices. So the advantages using this is we have much cleaner separation. The use of state classes and they being self-contained leads to a cleaner separation of states. It localized state-specific behavior into each class and partitions behavior for different states. The state pattern puts all the behavior associated with a particular state into one object. So each object or each class is responsible for its functionality. And the biggest advantage is you can test those states independently. Unit test those states independently and have much more confidence that everything will look fine. Because of all the state-specific code lives in a state subclass, new states and transitions can be added much easier as compared to enums by defining new subclasses. It makes state transitions explicit. We utilize RAI here because if you see, the devices are properly set, or all the state variables are properly set when the state comes into existence. And as soon as it goes out, even though we are not resetting in external devices because next state will be responsible for that, but it resets all its member variables. So that's, yeah. The disadvantages is we are using heap allocation. There are ways to minimize the heap allocation. So rather than creating states every time, you can create the states once, but then you have to provide the functions on enter and on exit. So you are not using RAI in that case, but you can still do that if heap allocation is the only concern. The concern I had is virtual functions. Generally, I try to minimize. So this state pattern relies on the fact that you have to use virtual functions because the interface is defined by the base state, and that interface has to be implemented by the actual concrete states. Every time when a new event comes, we have to add a new virtual function. That means even though it provides the base class provides the implementation where it says I'm ignoring that event. So it's still, what happened? Yeah. So it's still, some work is required, but much better than the last implementation we have seen. Okay. So now we move to the fun part. Finite machines using standard variant. So we will use variant of all the states to hold one of our state at a time. So as you know, variant, you tell that this particular object can hold these type of objects, but at a time only one object is there in that. So that is what even our finite state machine says, that you can be in any of these states, but only one state is active. So we will be utilizing that. So we know there is no need of virtual functions. But in my implementation, to ease some of the stuff, I'm using the base class, but not virtually. There is no virtual function on the base class. It's just to keep hold of context at one place. And other thing, in our implementation using state pattern, if I don't need a transition, what technique we applied? We used an invalid unit pointer. What is in C++17 we can use? That either it has a value or it not.
Optional.
So we will be using standard optional as the return type of the event handlers. So if there is no need of a transition, we will return a null optional. Otherwise, we will put value into that optional. This is the state you need to move on to. So we'll be using standard variant and standard optional here. So our variant is, we are a variant of 5 class types: load, payment processing, payment failed, payment success, unload. And optional, as I told you, will be optional on these states. Okay. So the base state is now very simple. It just has a constructor where it actually caches the context which was passed during the construction. And again, we are using the template machinery, generation machinery, to generate process functions for each kind of event. The only caveat is you can't inline this, you can't define this function here. This can only be defined once all the states have been defined. So this template definition has to go at the last once. So you will have a base state. All your derived states will derive from this, so they need this definition. After that, in your header file, you have to define this function has to go at the last, once you have the definition of the base state as well as all the derived states. So that is the one caveat you have to be aware of. Any questions on this?
Excuse me, I'm sorry. I guess I'm not following. Why does it need to be last?
Okay. So here it is generating an object of opt state. So to generate an object of opt state, it needs to know what all states I am, because it knows. So it needs the definition of all those derived states. So, okay. So lot again becomes very simple. You simply set at the transaction time the devices to their external devices to their proper state. And I am only interested in processing card event. Okay. So what I will only implement is process card presented event. For rest, I will say, please bring in process functions from the base class, which is just returning standard null optional. Any questions on this? If I don't do this, those process functions are hidden. So either I have to copy the template in each derived state, or I can just say using from the base state. So it brings in all the other process functions which will be generated by the base state into the visibility. So everything seems very simple now. It's just the constructor, what all state variables you need, and only define the functions which you are interested in. So this is the payment processing, which is one of the complex classes we have. So it's the same thing like what we were doing there, but these are not virtual functions anymore. Payment fail, same way. It sets the things properly, only interested in timeout event. Payment success sets the things properly, interested in 2 events, person passed and timeout. Unload, only interested in person passed event, and sets the things properly. So this is the whole state looks like. Now, I'm making it a templated state machine on the type of the states your system can have, so that it is a generalized solution. So when you are creating instance of it, you tell me that which states you are interested in, because that variant needs those states at last if you the private variable. Where is the mouse pointer? Yeah. So this needs all the states. And you also need to provide me the initial state, that which is my initial state. Because my system, as soon as it is up, the invariant is it has to be in the one of the states, and you have to tell me that which is that state. One assumption we can take is it can be the first state, but then its constructor can't be trivially constructible, might be. So then you have to provide me that state, and the state is set to the state member variable is initialized with that state. And again, we are then using template generation machinery to generate process function on this templated class. And it simply does is, whatever is the state, it calls process function on that. So if you see here, it uses visitor pattern to simply get the state, whichever is current state, and call state.process on it. That's it. And if you haven't noticed here, in all these things, all my finite state machine implementation is totally obvious to events. It doesn't know any event. One event can be a struct, other event can be class, third can be integer, fourth can be double, anything. There is no coding of event type in this. And this is how we are going to use our, this is our top level actual finite state machine. So it will have all the external devices, and it simply passes the process event to our templated FSM engine, which is templated on these 5 states. It's as simple as that. So you can reuse this templated finite state machine anywhere where you have those. The only function those states needs to have is a process function, and just process that event whichever they are interested in. Any questions on this? Okay. So I'm a bit happy with this implementation, as it's seen from the picture, because it provides all the advantages we previously had, but there is no heap allocation. There is no virtual functions. Everything is on the thing. The only disadvantage I have seen is, first thing, you have to be careful about the order, as I told you, where one function has to be defined. Only after all the derived states have been defined. That is one thing you have to keep in mind. The other thing is, initially when you are implementing, there were some compile time errors because you are fiddling with the templates. And anytime the compile time error you get, you have to go through a whole lines of error messages to figure out what actually the problem is. But once it is there in place, you don't have any problem. Any questions till now? So I'm excited that way it came out. But are we done yet? I think you brought up that. What about transition tables while we were discussing a couple of days back? How about transition tables? This implementation forces us to code the transition into the states itself. Okay. But I want an implementation where I can just plug in an external transition table. States don't care about transitions. They are only concerned about that once I'm in this state, what should be external devices state, and what are my state member variables. That's it. I don't want to have that process events. How we can do that? So we can code external transitions in a separate object. So all the process functions we can remove from our states, otherwise the state remains same. And the external transitions are in a separate object. And how that separate object looks like? A simple transition table. So it has all the transitions. So we are having the crawl operator, which states a state, and the event and tell me what to do. The only change is required is, if you notice, is in when the state is payment processing and we have a timeout event. There I need to delegate one functionality to the state, which is please try retry. Or that function name might not be, that is just retry. Means state knows that what is my retry count. So it just say, please try another thing. And if it returns true, that means I'm still in the same state. But if the state says, no, I'm done, I can't do anything more, then it says, okay, I'm failed. I should move to the payment field. But other than that, all the things are there, coded in this object. There is something loose here. Sorry for that. And if you notice, the last crawl operator, it generates definitions for all the state and event combinations I'm not interested in. So you just code the things you are interested in and let this last crawl operator handle everything else, which is just returning an empty optional. That's it. But how we plug in into this, into our implementation. As I told, payment processing needs some change. From this, it changes to this thing. So all the process function goes away. We introduce another function, try, retry, and which just checks retry count, either initiates transaction, restarts the timeout manager, and return true. Or otherwise, if I'm more than that, I return false. That's the only change required here. Otherwise, for all the other classes which we have seen, the process function goes away. That's it. And how we can use that? So now we also templatize on transitions. So the first parameter is, when we are templatizing this class, is transitions. And rest are states, that what all states are there. And the changes in the process function, what we are doing is, we get using visitor pattern, we get the state, but rather than calling state.process on the transitions, we are calling the call operator with the state and with the event. That's it. So on the transition object which you have provided me, I will use it, delegate it, that please handle this state and pass the parameter state and the event. And it gets the job done. And if you see my actual class, FSM class, which was actually having all that stuff, it doesn't need to do any change. It just provides the external transition. So if you see here, the TFMS here, its first pass providing me a transition table. And then the states and transition table is it's a trivially constructible. You don't even need to pass. You can have a constructor which doesn't even need that. So it has all the advantages which we had previously. The states become much more pure and don't have to deal with state transitions. Sorry, not code transition. It should be state transitions. Transitions are coded separately. Disadvantages remain the same, what we had last, that the definition has to go at the end and compile time errors you might run. So this gives us the toolkit where we had a generalized state machine where states were handling the transitions, and the other one where we can plug in the external transitions. I'm happy with what progress we have made, but engineer in me or an architect in me say, there is something better we can do. We are not following DRY. In both the implementations, if you see, this was the implementation using transitions, external transition, and this is the implementation using just states. If you see, there is a lot of same code, even though it is very less. But what we can do? So we can pick up this transition class, add another abstraction on top of that, generally we call policy-based design pattern, and plug in, rather than a transition, I will say, I need a strategy. please provide me a strategy how to handle this thing. And in my base class of this, so I'm calling it TFSM base, you give me the strategy along with the initial state. And that strategy has a function called execute, if you see here in the visitor pattern. And rather than me doing anything, I will say to delegate that functionality to the strategy's execute function, that this is the state, this is the event, let me know what to do. Give me a standard optional of the states, and rest is same. And these are the two strategies. One is external strategies, which is templated on transitions. So you need to provide the transitions that which you need. And in its execute functions, it does the same thing what we were doing in previous implementation. Transitions.crawl operator, this is the state, this is the event. And in strategy, which is states handling transitions, I just call state.process. And now, this is how TFSM state transitions, it inherits from TFSM base and plugs in the strategy, the state handling strategy. And for external transitions, the client has to provide me the transitions object, and I just pushes that down, and that's it. So there is no DRY, a single templated class which handles both the strategies. In my implementation, I even had a third strategy where FSM has the top level class has the transitions as member functions. So that can be done, but it's almost the same. But these are the two things generally we come up where either states know that what transition needs to happen, or we want to include into a separate table. Any questions on this? I know it's a lot of template and this thing, but so now I'm very, very happy. Now it looks good. Yeah. But what about performance? How do you think we stand with respect to performance? Any guesses? So if you have to rate enum, state, pattern, and variants, where we are, in which order, which is more performant? Yeah, go ahead.
Enum is the fastest.
Okay.
I believe the one with the enums is the fastest, and this is, I don't know how it compares to the virtual functions.
So no, so you said enum is the fastest.
Yes.
Second, which one is? So we have three: enums, state pattern, variant. Your guess is?
Oh yeah, I was going to say probably enums and variants are like the same, and then inheritance is the worst.
That's what I wanted. That's what I wanted. That's what, when I started writing, that's what my goal was. But I wrote a benchmark test using Doodle benchmark. So here I'm simply doing this. I start with the lot state, gets a chart presented, generates 2 timeout, then give a transaction success, timeout, person passed. And that was my benchmark test. Okay. So the first one is enums, the second is state pattern, and third is with standard variant. Standard variant is 90% faster than state pattern. Very good. But we are 7% slower than enums. I wanted to be at par with enums. Why the hell I am slower than enums? Any guesses? I did drop a hint when we said what was the problem with enums implementation. In my implementation, what was when we encountered it? We were not dealing with timers there. We were not using the timeout manager there in that classes, if you remember. So when these numbers came, I was a little bit disappointed. So I started figuring out what the problem is. As soon as I took that out, so these results become skewed. They are not comparison of apples versus apples. So let's take timeout manager out from everyone. And now we are in almost 20 runs I did with benchmark. We were approximately 2% faster than enums. I don't know why, but I was happy. And 24 times faster than state pattern. So we designed and implemented a solution which is much more flexible. There is no overhead when you want to add new event. Okay. Plus, it is able to cater to both our strategies, whether we want states to handle our transitions or whether we want external table to handle our transitions. Plus, all the advantages we have seen that there is no virtual functions, there is no dynamic allocation. Our system is algebraic sum type, so we don't have to worry about resetting something, forward or all that stuff. Our states can be easily unit tested in isolation. You don't have to worry about that. So this was what I implemented, and so all the code test benchmarks are available at this repository. There's a include folder which has all the templated classes. Tests have all the classes which we defined for turnstile example. Benchmarks test all the 3 implementations. The only thing is I was a little bit lazy to update the README, but it is CMake based. So there are build.batch file and build.sh file which you can use on Mac or on Windows to play around with. By default, I think benchmark is false, so benchmark is not included in that, but there is a setting enable benchmark, something like that, with which you can, if you are ever trying it out, you can even run the benchmarks on your system. Any questions?
So
Yep.
in the last implementation, the one with the transition table, do you still need a base state?
That is just to have the context, that reference to the actual class which has a, which can provide me reference to the external devices. Otherwise, you don't need. There is no use of base class per se that we need a base class. It's just that the common stuff. For example, I'm implementing that using the template machinery to generate a default implementation for all the state event combinations to say that return null optional. That can be coded in the actual classes itself. That is just 3 lines of code. For example, if you see, sorry. One minute, let me go to the base class. Yes, see, it is just there to have this context and to provide a default implementation for this. If you take the base state out, even that limitation that this must be defined after all state definitions, you don't need. You can just put this code in each base class. There is no runtime penalty, no binary size penalty. The only thing is why to repeat that code even in multiple places. That was the only.
Right, because in the one with the lookup tables, you don't, the transition tables, you don't really have a process method anymore, right? You don't
Process method, yeah, in that we don't have process methods, yes. So there the only purpose it solves is have a common place where the common things for all the states, for example, context in our case, right, that can be placed, that's it. Otherwise there is no need for a base state. Any more questions?
So are you saying that this base state inheritance could have been private?
Yeah, I don't need yeah, it can be private, yes. The only thing is as soon as you make it private, in this thing, how you can bring private methods out into the public, into the public one. So then you can't use this. So that's the reason. But as I said, base state is just to make me write a little bit less code, but there is no need. You can copy those 2 lines and you are good. And there can be scenario that in a couple of states, you don't even need context. So that's fine. So you can actually, in that case, do it that way. So there is no, the generic class doesn't rely on that you need to have a base class. It just relies that it can be any different. You don't have to adhere to any specific interface. The states can be totally independent. It doesn't even care about the events. The states or the transition table defines that what kind of event types are there. again, there also there is no restriction. You can have plain old data structures. You can have int, double, float, whatever you want. Because this whole thing is written in a generic way, so there is no interface with which it needs to work with. It's quite open to those things.
Could you speak a little bit more to the negatives? You mentioned a couple of possible.
Of what?
Still, of the variant, right? There were two things, which was in that list.
So that are not narratives in the sense once you are done with this, for example, or if you are using the base class. First time when I was putting the template, I wanted to write the template definition there itself. But I have to move it out of the class and make sure that it is defined after all my derived classes are defined. Otherwise, you keep getting on errors, compile time errors. And it was hard to debug that what is happening, what is not happening the way it is supposed to. And then, if you want to do some changes on top of that, you might run into compile time errors, which relate to templates. So that is the only thing. Compilation, all the things you are dealing with are compilation errors, because our template don't generate good errors that what we are doing wrong in our code.
Right. The order of definition disadvantage there, would that go away without the basic?
Yes, then you don't need, then that goes away, yeah. Any questions? So thanks for coming. It was pleasure sharing my experience with you guys. I hope go ahead.
I was going to ask about the benchmark.
Yeah.
So were those benchmarks done with like the 5 states that you've been working with? Or
yeah. So
how many states?
It doesn't grow payment failed one. Otherwise, it grows through other 4 states. So if I say, so this turnstile has 5 states. So we start with LOD, we move to payment processing, we move to payment success, and we move to unload.
Right. What I'm asking is, like, you're building like a generic FSM, right? And so have you tried benchmarking with like many states?
I have benchmarked with my own, actually the problems which I solved, and the results were same almost. So it's because those states are common, whether we are using it in enums or state patterns or this, the states are same. We are using the same classes for the states in all the 3 implementations. So there it doesn't make any difference.
No, I understand that it was the same for your use case
in
5 states. I'm just saying, like, have you tried? Because it's not like this is built for 5 states. This can handle.
Oh yeah, it can handle. Mine is like almost 11 states.
Okay.
My actual system is using 11 states.
Okay. And so did you benchmark?
Yeah, with that, yeah.
4 states and it was still good?
Yeah, because variant, what variant is? Initially, it needs to know the size of the largest size it needs. Mm-hmm. Next, what it does, it calls a destructor, whatever is the previous thing, moves the things into the new thing, calls the constructor, that's it. So,
well, I thought you were benchmarking basically the sequence of visit calls, right?
yeah, actually it is visit calls because that's what process my right now is doing. But what I'm saying is, whether you are implementing with state pattern, the rest of the code is same. We are using the same states. The only thing is how we are using them. We are not using any virtual functions anymore. We are not doing heap allocation. So that is where we gain performance.
Yeah, I think I follow that part.
So can you be specific that what exactly you are?
Well, each process calls a std visit, right?
Yes.
Okay, and what I'm saying is, for enum, the transitions are more direct than the std visit call.
Yeah, but if you see, compiler actually does a lot of, takes away all that boilerplate code in release. So never run benchmarks on debug. On debug, variant is slow as compared to enums. But as I started running my benchmarks on release, they were almost same or better. So, yeah, you had a question over there.
Oh yeah, I was just thinking about the benchmark between like variants and enums. Like you said that the variant has to hold the largest size. Do you think that the performance would get worse for variant if you have one state, for example, that is very data heavy, and then a bunch of states that are basically empty structs, and basically the entire time you have to carry around like a bunch of data you're not using in the variant machine.
So in enum, actually we are better than enum with respect to memory footprint because that's a product type.
It's really the inheritance one that.
Yeah, inheritance one, you can say, but the cost which, so let's say whenever, even for one time we are in that state. So on heap, we are creating that.
Yeah.
But later you say that I'm releasing that thing.
Right.
So there, if that state is very heavy,
Yeah.
I understand that this has, the variant will take. But again, the variant is on stack, not on heap.
Yeah. Like if you have a state, for example, that's very rare, that's very big, and
I haven't thought about it, but yeah.
99% of the
Yeah.
time you're in a very small
Yes.
state, maybe the inheritance will win in that.
Yes, might be. Yeah. But in that case, what, rather than using inheritance pattern, why don't we create a, in our state, we put a structure and create a object on heap for that internal structure. Yeah.
That's a good point.
Yeah. So then you reap the benefit of variant also, plus you don't end up having such a huge variant in one.
That makes
Yeah.
sense.
Yeah.
So you mentioned in the beginning about the use of MPART, Michael's variant implementation. I was wondering, do you have any benchmarking like results with the use of that implementation and the standard variant? Because I know that.
Sorry, I actually, so we were using MPART variant around about 6 months back. Then we moved our whole code to C++17. But we can run that. The only thing is, you can't use standard visit. You have to use MPART colon visit. That is the only change required, and rather than using standard variant wherever you use. But yeah, we can run that. Yeah. But again, I will say that is a transient change. Eventually, everyone will move to C++17, which has standard variant. So even if right now there is some performance degradation because of that, I will still take that hit rather than going to state patterns or to using virtual functions and heap allocations.
Oh, it's interesting. We've observed that the use of MPART variant is better in some cases than STD variant.
Okay, might be. I haven't benchmarked MPART variant. When I started, I didn't have C++17. So I used MPART and I used standard optional from some other implementation, I don't remember. But eventually we were allowed to move to C++17 standard and I am no longer using. Yeah, go ahead.
So it is faster in a lot of cases because the visit, so MPART visit will use switches to do the visit, as opposed to std visit, depending on what implementation you're using. libc++, for example, will do a function table, and it has to go through a function pointer to do the invocation. And a lot of times the inliners, the optimizers actually have a hard time looking through the function pointers. And so yeah, I've heard multiple people tell me that my variant is faster.
Yeah, so what I have seen in debug mode, standard variant always perform far worse than enums and all that stuff. Switches, enums I'm saying, switches. But as soon as I move to release, both on Windows and Mac, because that's my primary platforms where I code and then run all my unit tests, there it performs almost same, or I don't know why I am getting 2%. So I was surprised even that 2% difference. So I ran it 10, 15 times, every time it was almost same. So I didn't know the reason, but yeah, it should be same. As you said, it should be same. Yeah.
You mentioned that the error messages with the variant implementation can be really bad because of the templates. Could C++20's concepts improve on that? So if you didn't use generic templates but you use concepts there, would that improve or that?
No, so concepts will not help me there. I am just using template generation. If I have auto, then even the template type name is not required. I can simply use auto. that is generating code for me. I'm not restricting my interface. Concepts is more for restricting that only these things are allowed in my use. Here I'm saying that please generate a function where first parameter can be anything, second parameter can be anything, and it returns a standard optional, which is a well-defined that this standard optional, what I have defined is like opt state, something like that. So I'm using generation engine rather than restricting my functions to be only specific to these things. So I don't think so concepts will do anything for me in that case.
Wait, are you asking about using concepts inside for the variant implementation or for his stuff?
For the variant notation, I believe that's possible too. I asked in general because usually if you have two error messages with templates, concepts can help sometimes. Not usually.
I haven't looked into that, but yeah. Anything else, guys?
In this case.
Yeah. Yep.
It's a small question, but is there a reason why you use optional variant as opposed to putting monostate in the variant?
So that is the return. You are right that my state variant, the first can be monostate, and like rather than using standard option. But then I didn't wanted my variant of states to have a monostate just for return that I want to indicate that, oh, don't transition to anything else. But yeah, I tend to use that. But I thought that it's better to have them separated. States should only have those valid states which I am in. There should not be a monostate. While returning, I can rely on standard optional rather than putting the monostate in that variant itself. It can be done, means there is no harm in doing that, but I thought it's better to separate those things out. Don't use the same type for indicating that there is no transition needed.
Oh, I see.
Yeah.
Because I see. So the empty state isn't one of the states.
Yes.
It's just whether there is a transition or not.
Yeah.
And so you're separating those concerns. Yeah.
Yeah.
Cool.
Any more questions? Thank you then. You have 28 minutes on for your, or 18 minutes. Yeah, thank you.